Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss very important concept of magnetic field, that whether magnetic field obeys Newton's third law, or whether magnetic field or magnetic force obeys the law of conservation of momentums. So first of all, let us find out the magnetic field due to a moving charge at some point P. So you can see that this is a moving charge Q that is moving with a with a velocity V, and this angle is theta, where theta is the angle between this radius vector and this velocity vector. This velocity vector is the direction of velocity, and radius vector is the position vector of that point with respect to this charge at which we have to find out the magnetic field intensity. So we know that according to Biot-Savart law, dB is equal to mu naught by 4 pi I dl sine theta upon r square. This is Biot-Savart law in scalar form, and in vector form dB vector is equal to mu naught by 4 pi I dl cross r divided by r cube. Okay, now we can say that if this charge q is moving by a small distance dl, then the current produced will be q by dt, where dt is the time in moving this small distance dl. So dB will be equal to mu naught by 4 pi I, and dl I can be written as q by dt, and this will be dl cross r vector divided by r cube. So dB will be equal to mu naught by 4 pi r cube, and q and dl by dt is velocity v cross r. So this is the magnetic field in vector form due to a moving charge q. If this charge is negative, then the direction of magnetic field will reverse, and obviously we know that the direction of magnetic field will be in the perpendicular direction of the plane containing V and R. So in this case, V is like that and R is like that, and they both are situated in this plane of the screen. So if we find out the direction of V cross R, then V cross R will be inside the plane, and you can rotate the fingers of your right hand starting from V and towards R, and you can find the position of your thumb of the same right hand pointing inside the plane of the screen. So we can say that the magnetic field at point P is inwards. Okay, so this will be the magnetic field. Now let us also discuss a very important question which is very huge confusion among the students, that whether magnetic field obeys Newton's third law, and whether magnetic force obeys the law of conservation of angular momentum and linear momentum. So to discuss this very important concept, let us consider these two charges. You can see that there are two charges. This is q, this is q. They both are equal, and this q is moving with the velocity v1 in this direction, and this q is moving with the velocity v2 in this direction. So the direction of velocity of v2 is exactly towards this charge q, and if we draw a radius vector, then this radius vector will be, this is the radius vector, and this radius vector will be pointing exactly towards this charge q. Okay, so now if we find out, let us name that this charge is, if let's suppose q1, and this charge is q2. Okay, so now let us find out the magnetic force acting on q1. So first of all, we know that any magnetic force acting on Q1 will be due to the magnetic field created by Q2 on Q1. So if B12 is the magnetic field due to charge, or let us name it as B21. So it is the magnetic field due to 2 on 1. Then obviously B21 will be 0, because you can see that the velocity of this charge V2 and the position vector of this point where we have to find out the magnetic field are parallel to each other. R is parallel to V2, which in fact these are parallel, therefore their cross product will be 0, because R is parallel to V2. So it means that there will be no magnetic field on Q1, but the magnetic field B12 is the magnetic field on 2 due to 1. So magnetic field on 2 due to 1 will be calculated by drawing another R vector. This is let's suppose minus R vector. Okay. So B12 will be equal to mu naught by 4 pi into Q V cross R. Now V is the velocity of Q1, which is V1, cross minus R vector, and you can see that upon R cube, and you can see that obviously V1 and R vector are mutually perpendicular. So B12 will be, if we talk about the magnitude only, so B12 will be equal to mu naught by 4 pi Q V1 by R square, and the cross product will yield sine theta, and theta will be 90, and therefore sine 90 will be 1. So you can see that magnetic field on 2 due to 1, magnetic field on 2 due to 1 is non-zero, although magnetic field on 1 due to 2 is 0. So we can say that force acting on F12 will be the force acting on 2 due to 1 will be equal to QVB, and Q is Q2, V is V2, and B is inside the plane, so it would be B12, and the angle between B and V will be 90 degree, and sine 90 is 1. So F12 is equal to Q2, V2 and B12. Now the direction of this magnetic field, first of all, is inside the plane. The magnetic field is inside the plane on Q2 due to Q1, and the force acting on this charge Q2 due to this magnetic field will be calculated by the Fleming's left hand rule. Now you know that by using the Fleming's left hand rule you can predict the direction of force, and the direction of force will be like that, F12. Although the direction of the magnitude of force on 1 due to 2, F21, is 0, because there is no magnetic field acting on Q1. So there is a question that arises from this discussion, that how it is happening that the force applied by 2 on 1 is 0, and the force applied by 1 on 2 is non-zero, as this is not obeying the Newton's third law, because Newton's third law states that the force internal forces are equal and opposite, and they are equal in magnitude and opposite in direction. But these forces are not obeying the Newton's third law. As well as if you find out the net force acting on the system, So the net force acting on the system is non-zero. If we consider these two as a system, then the net force acting on this system is non-zero. Although external force of the system is zero, there is no force acting on the system from outside. So external force is zero and momentum should be conserved, but this momentum is obviously not conserved because net force is non-zero due to the fact that internal forces are not cancelling each other, as the internal forces are not obeying the Newton's third law. So this is a very important question. I will be answering this question in the video, in the same video, in this video, but let us discuss another problem. So first, now you can see that if we take different scenario, then let us first of all draw that this is R12 and this is R21. And obviously if this angle is theta, then we can say that the magnetic field on 1 due to 2 is, let's suppose B12 will be equal to mu naught by 4 pi and Q2, and velocity of Q2 is V2 cross with R12 divided by R. Let us write R21 and R12 equal in magnitude and equal to R, so divided by R cube. So B12 will be equal to mu naught Q2 by 4 pi R square and V2, and the angle between V2 and R12 is theta, the same angle theta, so there will be a sine theta, and the direction of this magnetic field will be outside the plane. So magnetic field on 1 due to 2 will be outside the plane B12. Okay, you can use Fleming's right hand screw rule and you can find out the direction of magnetic field. Although, and let us also find out the force on 1 due to 2. So F12, let us write it down with the same color. So F12 will be equal to QVB, V cross B. So you can see that V is in this plane and B is outside the plane, and so angle would be equal to 90 degree, and the direction of force will be given by the Fleming's left hand rule, and obviously the force will be acting in the downward direction F12. So F12 will be Q1 into V1 into B12, and sine theta is 1 because theta is 90 degree. Okay, so this is the first case, and now you can also see that the torque of charge 1, the torque due to force 1 2 about Q2 is non-zero, because this force is creating some torque about this, and this torque will be like that clockwise. And now if we find out the direction of force on charge 2, so first of all let us find out the magnetic field on 2 due to 1. So B on 2 due to 1 will be equal to B21, and B21 will be given by mu naught by 4 pi. Now I am just writing down directly mu naught by 4 pi Q into V. Now V is V1 and this is V1, and cross with this vector R12, which is also equal to R, but this angle will be 180 minus theta, so it would be sine 180 minus theta, which is same as sine theta divided by R square. This is the magnetic field on 2 due to 1 and the force acting on 2. Now let us also find out the direction of this magnetic field. the direction of this magnetic field can be calculated by Fleming's right hand screw rule, and you can find out that direction of this magnetic field will be inside the plane. And now if we find out the direction of force acting on the charge Q2, then this force will be acting in the upward direction like that, F21. So F21 will be equal to mu naught by 4 pi Q, in fact QVB. So Q is Q2, V is V2, and B is B21, and angle is 90 degree. Now torque of this force F21 about origin, or let us also write it down as the torque about origin. So torque about origin will be 0 because this force is passing through this point. So you can see that the net torque of this force about origin is the net torque of this system about origin is non-zero, and hence angular momentum L is not conserved for system. Although there is no external torque acting on the system, tau external is 0. So this is against the law of conservation of angular momentum, which says that if the net external torque acting on the system is 0, then angular momentum of the system will be conserved. But in this case, angular momentum of the system is not conserved about any point, or for example, we are talking about the net torque about origin. So it is not conserved. So this magnetic force is also not obeying the law of conservation of angular momentum. And in the third scenario, we have already discussed that the force acting on 2 due to 1 will be 0 because the magnetic force on 2 due to 1 is 0, and the force acting on 1 due to 2 will be non-zero because the magnetic field on 1 due to 2 is non-zero. So why this force is not obeying the Newton's third law, which is the law of action reaction, as well as if we talk about these two wires, then we can say that if we talk about the small force acting on the wires, we will be discussing the force acting between the parallel wires in detail in the later part. But if we just see the magnetic field direction due to 1 on 2, then it would be in the downward direction inside the plane, and due to 2 on 1, then it would be in outward direction outside the plane. And the force acting on the wire 2 due to this magnetic field B1, and this is B2. So the force acting on the wire 2 due to B1 will be like that. This is F2, and the force acting on wire 1 due to this one, second wire, is F1. And you can see that these forces are opposite in directions, and I am telling you, which I would be proving in the later part of the magnetism, that these forces will be equal also, and they are obeying the Newton's third law. So in this case, Newton's third law is valid, but in this case, Newton's third law is not valid. So this is a very huge question of which is related with the confusions of the student, and let us now decode the solution of this thing. So we first of all know that why we call the complete electrostatics and magnetics as electromagnetic fields, and we should always remember that electromagnetic field is a single field, and its one dimension is electric field and its another dimension is magnetic field. This is just like the fact that when a block is kept on a ground, then we can say that ground is applying only a single force on the block, which is the net contact force, and that net contact force has two components. One is the normal reaction and other one is the friction. Now in some cases, you know that if a block is kept on a rough floor but it is not tending to move or it is not moving, then there would be no friction acting on the block, and therefore only normal reaction would be acting on the block. So the net contact force will be just the normal reaction. But if that block is about to move, or it is trying to move, or it is in fact moving, then we can say that the net contact force will be the vector sum of the normal reaction and the friction. We know this fact. And obviously, if someone says that the ground is applying two forces on the block, which is one is normal reaction and the other one is friction, so this would be wrong, because the ground is applying only one force, that is the net contact force on the block, and there are two components of that force. In the same way, we know that these charges are creating magnetic field around them, both of them, as well as these charges are creating electric fields around them. Both of them are creating electric fields and magnetic fields. So they both are interacting with each other by electromagnetic force, not just electric force or not just magnetic force. So what we can say that the net force applied by 2 on 1 is purely electromagnetic, and it is a single force, and the net force applied by 1 on 2 is purely electromagnetic and it is a single force. The one component of that force is electric and the other component of that force is magnetic. So if we have to conserve the momentum, then we should conserve the momentum for complete electromagnetic force, and not just due to the magnetic force only, or not just due to the electric force only. So all the Newton's laws are equally valid for these two charges if we are considering the total force, which is electromagnetic force. And in this case, as we have seen that the force applied by the charge Q1 on Q2 is F12, and the force applied by Q2 on Q1 is 0. So this is which we are talking about is only the magnetic force. So you can see that individually magnetic force is not following the Newton's third law, because we are trying to apply the Newton's third law for single magnetic force. That is only a component of net electromagnetic force. Indeed, what should we do is the fact that we should apply the Newton's third law or any law of conservation of momentum for the total electromagnetic force. So if we say that the total force acting on this Q2 is this magnetic, and some electric force will be acting on this charge Q2 also, and the force acting on the Q1 is not magnetic because magnetic force is 0. So the net electric force acting on this charge Q1 will be the net electromagnetic force on this charge Q1. But the net electromagnetic force acting on Q2 will be the net resultant force of magnetic force and electric force acting on Q2. So if we have to find out if we have to apply the conservation of momentum, or if we have to apply the Newton's third law and check the validity of action reaction law, so we have to consider electric forces also, and we can apply the law of conservation of angular momentum as well as law of conservation of linear momentum as well as Newton's third law for net electromagnetic force acting on both of them. And definitely we can say that net electromagnetic force acting on Q1 and net electromagnetic force acting on Q2 will be equal in magnitude and will be opposite in direction. Definitely. But we cannot predict the direction of electric force acting on them, because these charges are not static charges. and we cannot say that they would be interacting by Coulomb force, because Coulomb force is for electrostatic interactions. These are not static charges, so they are not interacting by electrostatic force. In fact, there will be a complicated electric field by both of them on each other, and therefore we cannot just easily predict the direction of electric field. But we can surely say that we cannot individually apply the Newton's laws for individual magnetic force acting on them or individual electric force acting on them. But we can apply the Newton's laws equally, and they will follow definitely the Newton's law if we are applying the Newton's law for the total electromagnetic force acting on Q1 as well as total electromagnetic force acting on Q2. Okay, in the same way, if we are just conserving the momentum due to the magnetic forces only, then obviously individually magnetic force will not be obeying the law of conservation of angular momentum or linear momentum. But as a whole, electromagnetic, if we know that electric field and magnetic fields both carry the momentum. So if we just sum up the momentums of both the fields, and if we try to apply the law of conservation of momentum, then we would find out that for both the fields, the total momentum of the system will be conserved. In the same way, if we talk about the law of conservation of angular momentum, then we can say that obviously this system is not obeying the law of conservation of angular momentum, due to the fact that we are applying the law of conservation of angular momentum in the wrong way, because we are applying the law of conservation of angular momentum only for the torque of magnetic forces. But if we also consider the torque of electric forces, like that in this case, if we consider the torque of electric forces also, or if we consider the net torque of electromagnetic force acting on Q1 and the net torque of electromagnetic force acting on Q2, then we will see that we can see that obviously the net electromagnetic force acting on Q2 will be passing from this point definitely. Therefore, the net torque of electromagnetic force on Q2 about origin will be 0. And we know that the angular momentum conservation law is valid for total electromagnetic force. So we can definitely say that the electromagnetic force acting on Q1 will be acting on this, the electromagnetic force acting on Q1 will be acting on this line, because the electromagnetic force acting on Q1 will be passing through this point, because its torque will be 0 about origin. Because these electromagnetic force are internal force of the system, and they obey the Newton's third law, as well as they will cancel out each other. So if they are cancelling each other, their torque about this point should be 0. So we can definitely say that the net torque on Q1 due to electromagnetic force about origin will be 0, and the net torque on Q2 due to electromagnetic force about origin will be 0. Therefore, the net torque of the system will be 0 about origin, and hence we can definitely say that this system is obeying the law of conservation of angular momentum, because net external torque acting on the system is 0, and therefore angular momentum will be conserved. So angular momentum of the system will be conserved about origin if we are considering the total torque of the electromagnetic force, and if we are not just considering the magnetic force torques and the electric force torques. So we can say that as the electric force and magnetic force are both carrying the electric fields, and magnetic fields are both carrying the momentums and angular momentums. Therefore, if we are applying the conservation laws for total electromagnetic force, then it would be equally valid. And in the same way, if we talk about this case, that we have already discussed that individually magnetic force is not obeying the Newton's third law, but if we consider the net electromagnetic force on Q2 and if we consider the net electromagnetic force on Q1, then they will be equal and opposite in magnitude and opposite in direction, and hence they would be following the law of conservation of angular momentum, linear momentum, and Newton's third law. But in this case, we know that individual magnetic force is obeying the law of conservation of angular momentum, linear momentum, and Newton's third law. This is due to the fact that we know that current carrying wires are electrically neutral, so they are not creating any electric field on each other. So there is no electric interactions between these two wires, and the net electromagnetic force on this wire and on this wire is the total magnetic force only. So what I can say, that the net electromagnetic force acting on this wire is completely the magnetic force acting on the wire, and the net electromagnetic force acting on this wire will be completely the magnetic force acting on this wire, because these wires are not interacting electrically, as they are electrically neutral, and hence we can say that individual magnetic force can obey all the conservation laws as well as Newton's third law, because these wires are not creating any electric fields. So I think that after this video you would be getting the answer of your mysterious question, that why individual magnetic force sometimes does not obey the Newton's third law. Okay, so the conclusion of this video is the fact that if we apply Newton's third law or any law of conservation of momentum, angular momentum, then we should apply it for total electromagnetic forces and not just for magnetic force or electric force. So we would find some cases like I discussed in this video, in which you would find that only magnetic force would not be obeying the Newton's third law, and only electric force will not be obeying the Newton's third law, because Newton's third law is valid for total electromagnetic force, and the total and the net force of the nature is electromagnetic, and electric and magnetic forces are two components or two forces which acts in different scenarios, or which dominates in different scenarios. So this was all in this video. We'll be meeting in the next video. See you soon. Thank you.